This is an example of a tidal current power problem, similar to one that you will find on assignment number 10. So it is similar to the wind turbine questions. We have tip speed ratios, we have efficiencies, but there's a little bit difference here. When we were treating the power in the wind, we just assumed a constant continuous wind speed, but in fact the current in tides, the speed of the water varies sinusoidally. So we have to take that into consideration. So something that you need to know if you are calculating average power for a sinusoidally varying function, it's 1/2 rho A, and then it's u cubed, but then you have to average u cubed. And remember, it's not u average cubed, it's u cubed average. And the definition of u cubed average is 1/pi integral from 0 to pi of u max sine omega t cubed dt. And I'll just give you the result. It's 4/3 pi u max cubed. Okay, so if you want the average power from a sinusoidally varying water current, that's what you use. So let's do the first question, number 1, the average. You'll remember this is similar to the RMS values that you have for voltage and current when they're varying sinusoidally, but this is just a little bit different. Okay, so we put the 4/3/pi out front, and then we have the usual 1/2 rho A, and now we can use u max cubed, where u max is the value that they give there, 2 meters per second. Okay, so we have to remember this is seawater, so the density we're going to use is 1025 kilograms per cubic meter. Area is pi times the radius, 5 meters over 2 squared. That's the swept area of the turbine blades. And now we can use the peak speed, 2 meters per second cubed. And when you work that out, you get 34.2 kilowatts. Okay, that's number 1. Number 2, what is the overall efficiency? So we have 75% of the Betz limit, so that's 0.75 times the Betz limit, which is the 0.593, actually, if you want to be more accurate. And then we have the drivetrain efficiency and the generator efficiency, so we just multiply them all together, and we get an overall efficiency of about 41%, so 0.406. And so the electric power here would be the total times that average. So we'd have 0.406 times 34.2 kilowatts for an electrical power of 13.9 kilowatts. It's not huge, but it is something. Okay, the third thing about tip speed ratio. So remember, tip speed ratio is lambda, and that's defined to be the speed of the tip of the blade over the speed of the water, the current. Okay, and so we have the rotational rate of the blades. So the tip speed is omega r, where omega is 40 RPM, which we have to convert to rads per second. So 2 pi rads per revolution times 1 minute per second, 60 seconds, times 5/2 meters. Okay, so that gives a tip speed. The outer speed of that turbine blade is going 10.47 meters per second. That's V tip. Okay, so that's if you got these 3 blades, and they're going around at omega. This is moving at V tip, the end of it. Okay, So we have a tip speed ratio then of 10.47 over 2 meters per second. The speed of the current, we'll just use max there. So we get 5.2. Very similar to the tip speed ratio of a wind turbine, even though the values for wind turbines are much, much larger. That ratio is still the same. Okay, that's it.